We'll begin our new unit by looking at polynomial functions and graphs of polynomial functions. So a couple of definitions right off the top. The first is a reminder that a polynomial is defined as a monomial or the sum of monomials with real number coefficients. And we also are concerned about this being written in standard form. In other words, there's one correct way, one properly accepted way in order to write polynomials, and that's with the highest degree term first and then in descending order of exponents from left to right. So the example given in the notes, 9x to the fifth minus x to the third plus 4x plus 7. So we see our highest exponent is 5, and then we move down from there. 3, remember a 4x with no exponent is like saying x to the first, and the constant is like saying an x to the 0 power. So a constant has a degree of 0. So when the polynomial is written in standard form, we also talk about the degree of the polynomial. The exponent of the first term is then the degree of the entire polynomial. We also many times are paying attention to the coefficient that's part of the first term. And that has a name that's known as the leading coefficient. And those two things, leading coefficient and degree of the polynomial, we'll come back to pay attention to a little bit later on. So a quick table with a summary of some common polynomial types. We just mentioned that a constant, just a number, has a degree of 0. So the standard form there would just be f of x equals a number. That's a horizontal line. A linear function has a degree of 1. Y equals mx plus b, so 2x plus 7. Quadratic has a degree of 2. Those are the ones we've been graphing and then solving equations. If the highest degree is 3, it's known as cubic. The highest degree 4 is quartic. The fifth degree is known as quintic, and after that they don't get special names. They're just degree 6, degree 7, and so forth. So let's practice a couple of things. The first is whether or not a function is a polynomial function. There's a couple of things about that, and one is that the coefficients are real numbers, and then secondarily is that the exponents are integers. And so if our examples 1 and 2, if it is in fact if it is a polynomial function, we want to write it in standard form. So take a look at number 1 and double check, are the coefficients real numbers and are all the exponents integers? So we have coefficients of 5, 2, and -1, and then nothing in front of that radical. How about our degrees? Let's look at the exponents. I have an x to the fourth, an x to the third, and x squared, and then square root x, which you recall can be written as x to the 1/2 power. So because we have a radical as part of a term, not a polynomial. How about an example number 2? So do we have real number coefficients, 1/4 x, -1/2 x to the third? They're fractions. They are real numbers, though. How about our exponents? X to the first, x to the third, and then the constant, which is x to the 0. So those are all integer exponents. So even though this one looks a little strange, it is in fact a polynomial function. So to write it in standard form, our highest degree first, it keeps its negative sign. So -1/2 x to the third. And the next highest degree is 1/4. That's positive. So plus 1/4 x, and then plus 5/8. Let's flip the script. Now, instead of recognizing a polynomial when it's written, I would like you to write a polynomial on your own. A cubic polynomial function with 4 terms, so its degree is 3, and the leading coefficient is 2. Go ahead and pause the video. Take a look at each of those words in the instructions. Think about what that would mean in terms of what the polynomial would look like, and go ahead and write one. And then you can restart the video and check as an example. So if we did do an example, 4 terms, so I know there's going to be something plus something, plus something minus something. Okay, the degree is 3, so its highest degree term is going to be x to the third. And then remember, the degrees are going to descend from there. So my next is going to be something x squared, and then something x, and then a constant. Leading coefficient is 2. So remember, the leading coefficient goes out front. After that, whatever coefficients that are real numbers, you can put whatever you want here. So plus 4x squared. I'm sorry, I left off the square there. Minus 3x plus 7 would be as an example. Yours may have looked slightly different, but as long as you had 2 and then your variable to the third power and then 3 more terms in descending order of exponent, then that definitely checks out as a cubic polynomial function, 4 terms, degree 3, leading coefficient of 2. So we had talked previously that the leading coefficient and the degree would become important to us. And as we talked a little bit in class last week, when we were dealing with quadratics and their graphs, which is a parabola, parabola has one turning point. It has a vertex, it's going to turn around once, and that's it. Well, the higher degree functions can actually turn around more than once. A linear function, which is degree 1, never turns around at all. And so we think about, well, which direction is this function pointing when x gets very large or gets very small? And we refer to that as the end behavior of the function. Sometimes it's written as up and down. In older math textbooks, they use the terminology positive infinity and negative infinity. So I'm going to use kind of a hybrid in our notes today so that you get exposure to both. So the end behavior is totally dependent on the degree of the function and the leading coefficient of the function. So this chart breaks it down. There's 4 possibilities. It can be both ends pointing up. It can be both ends pointing down. It could point down left and up right, or up left and down right. How do we know which is which? So as an example, we recognize this function, f of x equals x squared. Its leading coefficient is positive 1, which is positive, and the degree is even, 2. If that happens, f of x approaches positive infinity as x approaches negative infinity or positive infinity. What that means is, on the left-hand side of this graph, it's going to point up. The right-hand side of this graph is going to point up. How about if we have a negative leading coefficient, like y equals the opposite of x squared? Well, we recognize this graph as well, a parabola that opens down. And in this case, this happens to be f of x equals the opposite of x to the 4th, which is still an even-numbered exponent. So we look at this, it points down and down. F of x approaches negative infinity as x approaches positive infinity or negative infinity. The left side of this graph points down, the right side points down. So with an even degree, both ends are going to point in the same direction. It's just a matter of positive goes up, negative goes down. So that's relatively easy to keep straight. Sometimes my students have a little bit of a struggle with the odd degree. So when the degree is odd, for instance, f of x equals x to the 3rd power. Leading coefficient positive, degree is odd. The left-hand side of this graph points down, the right side points up. The older way of saying it is f of x approaches negative infinity as x approaches negative infinity. So as I go farther out on the x-axis to the left, the graph is going to continue to decrease in value. As I go farther to the right, it's going to increase. So as f of x approaches positive infinity, as x approaches positive infinity. How about if my leading coefficient is negative? Here's f of x equals negative x to the 5th. I can see that my left side is pointing up, my right side is pointing down. So let's do one for practice. Here's a blank grid and a polynomial, f of x equals x to the 3rd, a polynomial function. F of x equals x to the 3rd plus 2x squared plus x. So I'd like you to go ahead and substitute in these values of x. Fill out this table. We'll sketch the graph, and then we're going to describe the end behavior. So go ahead and pause the video, take a moment to start substituting in some values, and you can come back and check your work. So if you went ahead and substituted in your values, it would look something like this. So let's simplify these. Negative 3 to the 3rd is negative 27. 2 times negative 3 squared, that's 2 times 9 is 18. Negative 27 and 18 is negative 9. Plus negative 3, that gives negative 12. If I put 2 in here, that's negative 8. Plus 2 times 2 squared, 4, so that's positive 8, so that goes to 0. plus negative 2. If I substitute negative 1, I get negative 1 plus 2, that's positive 1, plus negative 1 gives 0. When I substitute 0 in, I get 0. When 1 goes in, 1 to the third is 1, plus 2 times 1 squared. 1 plus 2 is 3, plus 1 more makes 4. For 2, I have 8 plus 8. 16 plus 2 more is 18. And when 3 substitutes in, this graph really rockets. 27 plus 2 times 9, 18. 27 and 18. Right? So that's 45 plus 3 more makes 48. So let's go ahead and plot some of these points. We're just sketching this graph out. So negative 3, negative 12. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've got a point down here somewhere. Negative 2, negative 2. At negative 1, 0, 0, 0. At 1, we have positive 4. 1, 2, 3, 4. At 2, I'd have 18, which would be up here somewhere. So we're going to find out a little bit about what happens around this point of the graph when we get back together for the next section. But for right now, all you need to know is that if I have x to the third power, two things are going to happen. I know for sure that this turns around twice, and that it can cross the x-axis as many as 3 times. So this graph is going to come up, probably going to have a little waggle to it, and then up like such. So this isn't a perfect example. If you check this out with Desmos, you'd see it look something like this. This little waggle is not something really that you'd know to do unless you had it shown to you or unless you saw it on a Desmos graph. But we're most interested in the end behavior. So I know here that my leading coefficient is positive, which is 1. My degree is odd. It's 3. So checking my chart, if the degree is odd and the leading coefficient positive, end behavior is down to the left and up to the right, which is exactly what our graph looks like. So take a moment now that we've walked through these things and fill out your summary. 3 things that you learned today, 2 things you want to know more about, 1 big question you still have, and then there's space here at the bottom of the page for sketches, other connections to other classes, other thoughts.